The key thing for combinations, unlike permutations, is the order doesn't matter. You've already seen the formula, except here there's not supposed to be a line. That's just the other notation. Special cases, if you have n objects and you choose all n of them. I have 52 cards and I choose all 52. There's only one way to do that, if the order doesn't matter. If you have 52 cards and you choose one of them, there's 52 ways because you're choosing one of the ones from there. So we've seen some things like this before, that 10 choose 6 is the same as 10 choose 4. If I had 12 choose 7 is equal to 12 choose k, and k did not equal 7, what does k equal? K would equal 5. Because making a group of 7 from 12 means every time you make a group of 7, you're left with a group of 5. So counting groups of 7 is the same as counting groups of 5. If I had something like what's k? K is going to be 8. So you could do a guess and check there, but maybe you're starting to notice that these two, if they're going to be the same, if these things are going to be equal, then k plus k minus 3 has to equal, in this case, 13. If those two things add up to the number that you started with, they'll be equal. So then in this case, you'd have 2k minus 3 equals 13, 2k equals 16. So k would equal 8. So this concept that when you make a group, you're always left with another group of a different size, and those will be always equal to each other. 10 choose 6 is equal to 10 choose 4. We can see it in the formula, why that happens, and it makes sense logically as well. So one of the fun things about combination questions that don't come up in the textbook is we can solve poker questions. If you like watching poker on TV, or if you know how poker works at all, what happens is a poker hand is made up of 5 cards. So if you have a deck of cards and you are dealt 5 of them, take out the jokers. Okay, perfect. So I randomly pick 5 cards. 1, 2, 3, 4, 5. You'll probably never see this ever again in your entire life. Are you ready? The Queen of Spades, the Jack of Diamonds, the 9 of Spades, 8 of Clubs, and 4 of Spades. Okay, now for those of you that know poker, this is like the worst hand possible, all different. I mean, I have a high card that's a queen, but this is not a good hand at all. But what's amazing about this hand is the order doesn't matter. What's amazing about this hand is the chances of me getting this hand are like 1 in 2.6 million. If I tried to do this again, I'd never be able to get it again. The chances of me getting this exact hand are the same as me getting a royal flush in hearts. Of course, that would be more impressive because there's a 1 in 2.6 million chance of that as well. Well, where does that 2.6 million come in? If we count all of the poker hands possible, it's a combinations question. Order doesn't matter. We have 52 cards. We're trying to choose 5 of them. Ooh, and I think I've got this number memorized, give or take 3 digits. Which means I don't have it memorized. But I think it's close to, I don't know. How close am I? Someone have a calculator? Nobody quick? Oh, I got it. Nice. Good. So there's 2.6 million different poker hands, and this one that I just pulled out is one of those. So you just saw something that has a chance of 1 in 2.6 million. Of course, any hand I would pull out would be a 1 in 2.6 million. And the one that I got happens to be awful in poker. But we can now count different things in poker, and we can see why is it? Why is it that some hands in poker are worth more than other hands? And we'll look at some of those later in today's class. So another combinations question. Committee of 2 boys and 3 girls is to be selected from 15 boys and 18 girls. So you have 2 main decisions. You need to choose which 2 boys, and you need to choose which 3 girls. Does the order matter when choosing the boys? Is it going to be a different committee if I had chosen Ethan first and then Ethan? Or would it be different if I chose Ethan and then Ethan? Okay? So it's still the same committee. So the order doesn't matter. I have 15 boys. I need to choose 2 of them. I have 18 girls. I need to choose 3 of them. Do I multiply in between or do I add? I hear multiply and add at the same time. Should I do halfway? Like half the add sign and half the dots for multiply and divide instead?
Why not?
You multiply. So we add when it's cases, but a case needs to count the entire thing. So when I think about 15 choose 2, have I counted an entire committee of 5 people at that point? No. So it's not going to be a cases where we add. In fact, if I do choose Ethan and Ethan, every time they get grouped with a different set of 3 girls, it's a different committee. And so that's why it's multiplied together, because each group of 2 boys can go with each group of 3 girls, and that would make a unique group of 5. So you multiply this out, get a big number. We won't multiply it out right now. We'll just keep going with some more questions. A group of students is to be separated into 3 smaller groups. So if I decided I'm going to put you guys into 3 groups, but group A has 8, group B only has 5, and group C has 7, how many ways can this be done? The order doesn't matter in those groups. Well, how many ways could you pick group A? Is it just 8 factorial? 8 factorial means 8 people arranged in a row. Group A would be, how many people could be in group A? Anyone. There's 20 people in total, right? And I need to choose 8 of them to be in group A. Does that make sense? Now when I get to group B, if I choose group B next, how many people are left? 12. And I need to choose 8 of them. Group 5. Group B only has 5. And then when I get to group C, does it make sense that it'll be only one way to do that? Everybody who's left is going to be in group C. When you think about this, can you see that everybody still has a chance to be in any group? You could be chosen in group A, but you could be not chosen in group A. Could be chosen in group B next, but you could not be chosen in group B next.
It says order
Well, this one wouldn't need this, because if you're making a group, you have to ask yourself, if I'm in a group, does the order matter in how we were chosen? Or is it still the same group? It's going to still be the same group, right? If they're going to sit us on a park bench, all of a sudden the order does matter. But if it's just a group of people together, then the order doesn't matter. Now, would it have made a difference if I chose group B first and then group A and then group C? Should still, like, it shouldn't have mattered, but, and everybody would still have the same chance, but my numbers would look different, right? If I did group A first, I'd have 20C5, and then if I did group B next, I'd have 15C. So if I did B and then C and then A, choose 8 for A, would it make a difference? Or are those numbers the same? The answer is going to be the same. Still have the same, like logically it makes sense. Now mathematically, why does that happen? Well, if we look at the numbers here, this is going to give me 20 factorial over 12 factorial, 8 factorial. This is going to be 12 factorial over 5 factorial, 7 factorial. And this is going to be, well, 7 factorial over 7 factorial, 0 factorial, if I use the formula. And if I simplify this, can you see that your 12 factorials will cancel? And those would cancel. And you're left with 20 factorial over 8 factorial, 5 factorial, 7 factorial. If I look at this one, no, what's 0 factorial? 1. 15 factorial, 5 factorial, and then 15 factorial, 8 factorial, 7 factorial, and then 8 factorial, 8 factorial, 0 factorial. And this 15 is going to cancel out, and these 8s are going to cancel out, and the 0s equal to 1. Can you see that we have the same thing? Cool. What do those numbers remind you of when it's written that way? What kind of question? What kind? Repetition stuff, identical objects, like a Mississippi kind of question. Okay? And so, could we have solved this like a Mississippi type of question? If I lined you all up from shortest to tallest, and in a hat I put 8 A's, 5 B's, and 7 C's, and I got you to pick them out, every single arrangement five B's and 7 C's, right, would be 20 factorial over 8 factorial repetition of the A's, 5 factorial repetition of the B's, 7 factorial repetition of the C's. And the fact that those are identical objects takes the order out of the grouping. Interesting. So there's multiple ways we could think about this same question and come up with the same answer. Yeah, there's 7 of them there. You just couldn't see these last 2 because they were hiding. Yeah. You see them now? Yeah, so good. Okay. We're going to figure out the number of poker hands with no clubs. If I wanted to count the number of ways I could get no clubs, if I look through the deck and I took out all the clubs, oh, this is nice, they're all together, mostly. If I took out all the clubs, something amazing is going to happen. I'm going to give 5 cards to Ben, randomly. going to be magic. Did you get any clubs? You can take a look. No! Wow! Magic. How did I do that?
I don't know, maybe because there was no clubs.
Maybe because there was no clubs in the... If you take out the clubs, if I did it again,
Show it. Show the same card.
yeah, no clubs in here.
There's no diamonds in it too.
No, this is a diamond.
No, like in the hand.
Wow, that's also cool. But that could happen, a little harder to do that. But if I take out all the clubs, I now have only 39 cards. And every time I choose 5, what am I going to get? A hand with no clubs. And 39 choose 5. So I think this is a pretty cool number, if I remember. Yeah, look, it's a pretty number. That's how many hands have no clubs. Now, the problem with counting questions is that you can come up with something logical that makes sense to you that can be completely and utterly wrong. So what I'm going to do in this next question is I'm going to become a salesperson. I'm going to try and sell you 3 different methods for doing this. And I'm going to convince you that all 3 are right. Now, they might all 3 be right, and they might all 3 be wrong. Or 1 might be right, or 2 might be right. That's what you have to decide. But I'm going to try and sell you on the fact that all 3 of these methods are correct. Yeah, I'm going to film all 3, and I'm going to convince you that they're all right, right? Just like the rest of the unit, which I taught you stuff that wasn't true, you believe me. What's that? You convince yourself. Well, this is... I will tell you in the end which ones are right, and I will show you why one is right over another one. Don't worry, I'm not just going to leave you hanging forever. But to begin with, okay, we're going to talk about some strategies. And then you have to decide which ones you like and whether or not they're correct or not. Okay? So here is strategy number 1. I need to have at least 1 club. So what I do is I take the 13 clubs that I have and I choose one of them at random. 13, choose 1. This will give me 1 club. I then take the rest of these 12 cards, put them back in the deck, mix it up. I have 51 cards left. I need to choose 4 more. There's a possibility I get more clubs, but there's a possibility I don't get any more clubs. But I will be guaranteed to get at least 1 club. Okay? That's case number 1. Make sense? Of course it makes sense. They're all right. Okay? Number 2. Well, I've already figured out that there are 52 choose 5 as all the poker hands possible. And I just counted out the ones that have no clubs. That was 39 choose 5. If I subtract those 2, what would be left would be ones that have at least 1 club. Because I count all of them, I subtract the ones that have no clubs, what's left is at least 1 club. Okay? Method 3. I'm going to do it in cases. Case 1, I'm going to count how many hands have 1 club. Well, that's like before. I'm going to choose 13, choose 1. And from the other 39 cards that are left, I'm going to choose 4 of them. And that will count how many hands have exactly 1 club. And then I'm going to have to do case 2, with 2 clubs. So I have 13 clubs. I choose 2 of them. And from the other 39 cards left, I choose 3 more. Case 3. This one's a long one, but I picked 3 clubs, so I have 13 clubs. I choose 3 of them. And from the 39 left, I have to choose 2 more. How many more cases am I going to have? Case 4, 4 clubs. From the 13 clubs, I choose 4 of them. And then I choose 39, choose 1. And then finally, case 5 is the case where I happen to choose all 5 clubs. Since this is a cases question, I would figure out each of those separately and add them up to get my answer. So now the question for you is, I tried to convince you that all 3 were right. Are they all 3 right? Or all 3 wrong? Or 1 is right and 2 are wrong, or 2 are right and 1 is wrong. Okay? So the question is, what went wrong in the logic for the first one? Everything seemed right. I picked a club, then I picked more. Why did I get a number? Why is this number more than the possibilities, right? Because so let's find out why this is wrong. When I did 13 choose 1, which club did I pick? Just let's do an example. 7. So I picked the 7 of clubs. Okay? I put the other 12 clubs back in, and then in the 4 cards that I chose next, what's a possibility? What could I choose? 2 hearts, 3 diamonds, 4 spades, and the jack of clubs. Good. Now we're going to find out where the problem is. Because in my 13 choose 1, could I have also started and got the jack of clubs? Right? And then I put the other 12 back, and then I pick the 2 of hearts, the 3 of diamonds, the 4 of spades, and the 7 of clubs. In this method, these would be counted as different. But are they different poker hands? So what happened in method 1, whenever you're counting things separately, you have the possibility of adding order. Okay? Because you have 2 things together, it's fundamental counting principle, decision 1, decision 2. And in example 1, I have an overlap. I could have picked the 7 of clubs here, or I could have picked the 7 of clubs there. In which case, I get something like this, which are identical, but they're counted as different. And so we had a whole bunch of things we counted more than we wanted to, hence the number was more than the possible hands in total. In contrast to 3, can you see in this case and this case there is no overlap? When I choose clubs and then I choose other cards, I can't get the same card in both of those parts. And so each of those cases counted a different thing and added up, included all the ways to get at least 1 club. So we got to be a little bit careful with overlap. Now in the last 10 minutes, we are going to look at some other... Whoa, what?
Scroll down. Why is the second one correct?
Why is the second one right? Well, if you take all of your poker hands, right, and you happen to buy enough decks of cards so that you could lay them all out, all 2.6 million, and look at them, and then you went around and took out all the ones without clubs and put them aside, what would you be left with? Okay? Does that make sense? Okay, so I'm imagining 2.6 million poker hands all spread out all over the place. And then I go through those 2.6 million and I take out the 57,000 that have no clubs. What's going to be lying on the floor? Each of those ones that are left will have at least one club.
I don't know when time is all those electric, all the clubs. It's like I'll just find all the clubs.
No, this will give you at least one club because we're taking out all the ones without clubs, and then you'll be left. So strategy 2 is the most efficient. Using the not strategy in the combinations is the most efficient. The cases does work as well. Well, if you had, like how small? We could do it like with less cards, just using aces and twos. So if you take out all the aces and all the twos, and these will be clubs, diamonds, spades, hearts. And you want just hands of 2 cards. Okay? How many have at least 1 club? So does it make sense that 8 choose 2 is all the hands that are possible? That would include, right? We can see it be those 4, those 4, those 4, and those 4. How many does that make? Oh, and we also have to do, sorry, I need to color code this a little bit better. This ace could also go with these 3, right? And this ace could go with this one, and this one. And this ace could go with this one, and that one. And this ace could have gone with this one, and this one. That's a lot of drawing lines, but can you see that out of each ace that we could have picked, there's 7 lines coming out of them. Maybe you can't see them. And the 2s also could have gone with the other 2s. And out of each 2, there would be 7 lines connecting to all the other ones that they could go with. And so if each one has 7 lines coming out of it, and there's 8 of them, you'd get 8 times 7, which would be 56. But then you would have counted each group twice. So you'd have to divide by 2. And you get 28. Even on a small scale, it's a little bit big to think about. So there's 28 ways you can get 2 hands. How many of them have at least 1 club? Well, the bad ones would be 6 choose 2. Because there's 6, you take the clubs out, right? You take these ones out of the mix, and there's 6 cards that have no clubs. Choosing 2 of those, there'll be 15 hands without any clubs. And so in total, there's going to be 13 that have at least 1 club. Okay? Now, when counting those ones directly, can you see if you had exactly 1 club, this club could go with those 6, giving you 6. And then this club could have gone with those 6 to give you 6 more. And then what haven't I counted? Both clubs together, 1 more to get 13. All right, now, get our brains ready to count poker hands. We'll start off with something relatively simple and straightforward, and I'll teach you a strategy for counting some simple poker hands. Strategy doesn't work for all things, but it should work. It will work for a lot of them. So we're going to start we're going to start by counting. No, let's just do one pair. A poker hand with one pair, for example, would be like getting 2 aces and 3 other numbers that are different. What we're going to do when counting poker hands is we're going to count groups of numbers that are the same size at the same time. So what I mean is that the only pair that I have is the aces. But I have 3 single cards. So when I want to count this, when you're counting a pair of cards, the first thing you have to decide is, what is my pair of cards going to be in? Is it going to be a pair of aces, a pair of fives, a pair of sevens? Which pair am I going to pick? Well, there's 13 different numbers. I need to choose one of those numbers to be my pair. And if I choose aces, how many aces are there in the whole deck? 4. So once I choose which kind of card I'm going to pick, I need to say, well, there's 4 of those aces. I need to choose which 2 I'm going to pick. And this together will list all the different pairs that are possible in a deck of cards. The 13 choose one says, first of all, I'm going to decide what number I'm going to pick. And once I've decided on a number, I need to choose which 2 of that number I'm going to pick. So I have 4 choose 2. Well, because it could be a pair of aces, could be a pair of fives. When I'm counting how many total card hands from a poker deck have a single pair in them, I have to consider every single case that could be possible. This is just an example: 2 aces, a 5, a 7, and 8. That's one of them. I want to count every single hand that has a pair. Yes? Well, if you're wondering why is it when they're playing poker, how do they know that they have a winning hand? How do they know what's a good strategy to move forward or when not to? What are my chances at this moment, given everything that I can see, that I'm going to win? And those great poker players know that. They know when they for sure are going to win, and they change their strategies accordingly. They know when they have a 90% chance that they're going to win, and then they change their strategies. So they have to know the mathematics behind it. Now, this is going to say, why is it that different hands are worth more than others? How much better is one hand than another? No, this is just for interest sake. Okay. So now, if you have to pick 3 other numbers, since they're the same size, they're all single cards, they need to be chosen. There's 12 numbers left because you've already chosen one when you chose the pair. Aces are gone. You can't pick aces again because then you're going to get 3 of a kind. So there's 12 numbers left. You need to choose 3 of them. And then once you've chosen, say, 5s, 7s, and 8s, how many 5s are there? There's 4 of them. You need to pick which 5 you're going to take. There's 4 7s. You need to pick which one you're going to take. And there's 4 8s. You need to pick which one you're going to take. This together will give you 3 single cards.
Why is there 12 choose 3?
There's 13 different kinds of cards in the deck. If you've chosen one to be your pair, say aces, there's 12 other numbers left that could go with it. You need to choose 3 of them, and you need to choose them all at the same time, because getting a 5, a 7, and 8 isn't different from getting the 7, the 5, and the 8.
Yeah.
And then once you've chosen those 3 numbers, you have to say, well, which 5 are you going to have? Because there could be 5 of spades, 5 of clubs, 5 of diamonds, 5 of hearts.